We move on to the next video on Brownian motion as we consider the properties of Brownian motion, still talking generally about stochastic processes. Okay, like we saw in the previous video, a Brownian motion can also be called a Wiener process as we consider the history behind it, starting from Robert Brown to, was it Albert Einstein now? Then to Wiener, who came up with the idea of Wiener process. So by definition, Brownian motion, like we saw in the last video, stochastic process W of t, a collection of stochastic process W of t at time for time greater than or equal to zero, is called Brownian motion. If W of zero is zero, in the last video I said I used B of t a lot. So B of t is zero, that's the initial condition. Then you have independent increments such that Wt minus Ws is independent of the past for t greater than s. And then we have stationary increments such that W sub t minus W sub s is normally distributed with variance t minus s, like that. So, and then we have continuous paths. Then we move on to, so since we're talking about the properties, right? So we'll go straight to the properties. So the first property is Gaussian increments. So W sub t minus W of W sub s is normally distributed with mean zero and variance t minus s. That's simply t minus s. So example is to find the distribution of W5 minus W2. That means W5 minus W2 is normally distributed with mean zero. The mean is always zero, and variance 5 minus 2, that is 3. Okay, then we have property 2, which talks about expectation and variance. So the expectation of W sub t is 0, and the variance of W sub t is t, like we already saw before. Then that means the expected value of W4 is 0, and the variance of W4 is 4. Very straight to the point. And then we have property 3, talking about covariance structure. So if you talk about covariance of Ws, comma Wt, that will be the minimum of S and T. So covariance of W2 and W5 will simply be 2 easily. Okay. And then for property 4, where we have independent increments, if intervals do not overlap, Wt minus Ws is independent of Wv minus Wu that might have been before T and S. And then we have the scaling property that WCT is equal to square root of C W sub t. So that's some scaling going on right there. And then we have property 6 talking about the martingale property. We're going to study martingale, I think in the next video or so, or in a video after now. It talks about modeling fair games. So the expected value of W sub t given f of s, instead of being 0 now, because f of s is there now, it will be W of s for s that is less than t. Okay, then we have property 7 talking about quadratic variation. So the summation of the square of W sub ti plus 1 minus W sub t sub I is it approaches the time itself, right? That is quadratic variation. Summation, open bracket, Wt sub I plus 1 minus W sub t sub I, all raised to power 2, approaches time t. So it seems to approach the variance, right? That's the quadratic variation. And 43.9, we have the property 8, where that which is nowhere differentiability. So Brownian motion parts are continuous and they are nowhere differentiable, you know. So they're nowhere differentiable. And then we can then simulate. We have simulation of Brownian motion where we use the fact that W sub t plus delta t is equal to Wt plus square root of delta t multiplied by z, where z is normally distributed with mean 0 and variance 1. So then we can also do the simulation as we run this. So this is what it brings. Of course, as you keep running, it keeps changing for sure. So like, because it is a random process too. So we know Brownian motion is continuous and it is random, like that. So we have something like this. So you see, discover that everything we've been talking about, from random walk to Markov chains and everything, they tend to have the same kind of thing. And in the same kind of behavior, I mean. So, and in the last video, we saw that Brownian motion is random walk as the number of steps tend to infinity. So it's like the limit. Brownian motion is like the limit point of random walk. So like I said, if you keep running, it keeps changing like that. Okay. So we go for empirical mean and variance now. So we simulate many paths so we can verify that the expected value of any Brownian motion is actually zero and the variance of W sub t is actually t. So that's straight to the point. So here, if we run this now, so you already have that mean minus zero. You have something very close to zero in short. And then for variance, so here we take 10,000 steps. The time is one and n is 1,000. So we know mean is zero and time is always one. So we have n square root dt with all of that, all the randomness normally distributed. So mean is always hovering around zero and variance is hovering around one as expected because the time is one like that. Okay. So we move on from there and we talk about the empirical covariance. We already established that covariance will be the minimum of S and t, those being time steps for sure. So if we come here and we have time 0.2 and 0.5 and m is 5,000, n is 1,000 and all that, so we know that the covariance is going to be 0.2. That's already clear because the minimum of 0.2 and 0.5 is 0.2. So if you keep running it, the value keeps hovering around 0.2 like that. Okay, the smaller of 0.2 and 0.5. So whatever value you get can easily be rounded up to 0.2 like that. Okay, so we go for problem one now in that sense. Find the distribution of x, which is 3w sub 2 minus 2w sub 1. So the solution here, w sub 2 can be said to be w1 plus, it's we have steps, right? You have W1, W2, and so on. So W1 is the beginning. W2, the next step will be the difference between W2 and W1. So that's why we have W1 plus W2 minus W1. So in that case now, X is going to be 3 into W2, which is W1 plus W2 minus W1. This and then 2 W1 like that. So if you tidy things up, we have 3W1 plus 3W2 minus 3W1. So 3W1 will cancel minus 3W1 automatically. So we have 3W2 minus there's 3W1 here, right? And then there's 3W2 here. So by the time we tidy all of that up, we have W1 plus 3W2 minus. Okay, let me even do it straight. This 3W1 minus 3W1. That should go, right? And then we have 3W2 minus 2W1. Okay, so the deal here is that though this cancels out, but because we want to normalize this, right? For us to get uh for us to get 3 minus 3W1, we need an extra W1 to cancel that. So we have W1 plus 3W2 minus W1. So and since W1 is normally distributed with mean 0 and variance 1, and W2 minus W1 is normally distributed with time steps with mean 0 and variance 1, that is 2 minus 1. So all together, we can say that x is normally distributed with mean 0, all right, and variance 1 plus 9, variance 1 plus 9, like that. So we have 0, comma 10, like that. So x is normally distributed with mean 0 and variance 10. Okay. So we go for problem 2. So for problem two now, we want to find the expected value of omega W5 given W2. So and the solution would usually be expected value of W5 given W2, that's W2 like that. And then so that just goes very easily. And then for problem three, find the distribution of W2 given uh find the distribution of W5 given W2, which is equal to X, right? So W5, of course, we know that should be W2 plus W5 minus W2. That's like W2 cancels W2. So W5 given W2 now will be X, which is normally distributed with mean X. all right, and variance 3. That's 5 minus 2, 3, like that. Then we can also have joint distribution. That's W1, W2, and that has mean zero. Each of them has mean 0, 0. And because they are separate value stuff, right, then we can now have covariance matrix 1, 1, 1, 2. Okay, so like that for joint distribution. So, and then the key takeaways from here is, we have basically talked about properties of Brownian motion. So, key takeaways include that Brownian motion has Gaussian increments and variance W sub t is equal to t. Covariance Ws, comma Wt is the minimum between s and t, and it is a martingale, which you're going to discover very soon. It is used for modeling fair games, and then Brownian motion is continuous but nowhere differentiable. We've seen all of that, and we come to the practice problems. So the first five, find the distribution of W3. Of course, that would just be W3 is normally distributed with mean 0 and variance 3. That's all. Compute expected value of W5. Of course, that will simply be 0. And variance of W5, that's 5. Find the distribution of W7 minus W2. That will be normally distributed with mean 0 and variance 7 minus 2, which is 5. Then compute covariance of W3, W8. Take the smaller value. That's the minimum of 3 and 8, which is 3. Compute the correlation of W2 and W5. Okay. Did you see correlation before here? Um, okay. I think we just saw covariance. Okay. Covariance was what we saw there. So, um, then we have independent increments. Are W4 minus W2 and W6 minus W5 independent? Justify. Yeah, I think they are clearly dependent because they do not overlap. They do not overlap. Then these ones overlap because you have W3, W1, W2, W0. These are not independent as you can see. So because this is from 4 to 2 to 4, 5 to 6, no overlap. Then 1 to 3, 2 to 0, there's overlap like that. Okay. Then we have linear combinations. Find the distribution of x equals W2 plus W4. So we use the kind of process we saw the other time, and we can do that for these other ones. That's all the process of breaking it down, like what we did here, you know. So then we have conditional expectations, which we also saw there, and then conditional distributions. Find the distribution of W6 given W2 equals X, so that then covariance or correlation. We've not talked about correlation actually, so we have to um we'll have to maybe in a subsequent video that will be dealt with too. Then we have advanced concepts, show that WT is a martingale by verifying this. So we also saw that kind of process, show that the variance of WT minus WS is T minus S. Yeah, so with this, we are done looking at the properties of Brownian motion. Let me know how helpful this is for you. And there's something else you'd like me to try out. Feel very free to let me know. Don't forget to try your hands on the questions. So you have 1 to 5 here, then you have 6 and 7, you have 8 to 10, you have 11 to 13, 14 and 15, then you have 17, 16, 17, and 18 to 20. Try your hands on them and let's see how well you get the gist. If you have a problem with any of the questions, feel very free to let me know. So I might be able to make a separate video to address whatever question you like to solve, right? So, if you have subscribed already, I thank you very much for doing that. If you haven't subscribed, I will ask why you have not done that. So go ahead, subscribe, hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you special privileges like seeing some videos exclusively, or or getting to see some videos first before other people. You can also request for PDF copies of my notes. We can also hang out together to discuss whatever interests you on my channel. Ultimately, don't forget to comment, like, share, so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.